Hello and good day everyone. In this video, we would be solving for shear and moment diagrams for statically determinate beams. So suppose that we have this example. So we have here in this beam a 10 kilonewton per meter uniformly distributed load. We also have a 15 kilonewton point load or a concentrated load. And we also have a triangular load at this side of the beam. And in here, we have here a hinge support or a pin support if you may, and also a roller at this particular portion. Okay, so though it is already indicated earlier that we will be discussing about statically determinate trusses, or beams, I should say, we should first prove that this really is a statically determinate beam. So with that, our first step is for us to check the determinacy first. So in order for us to check the determinacy of a beam and also for frames, this is to be our formula. So in this formula, 3m plus r, that must be equal to 3j plus c. So that is for the determinacy of a beam and frames, actually. Okay, so what does M stand for? So M stands for members or for the number of spans. R is for the number of support reactions. And J is the number of joints. When we say number of joints, this is the separator for the number of members. Okay, so whenever you are to check for the determinacy, it would be better for you to disregard the loads first in order for you not to get confused. Okay, so what is now the value for M? So in this case, the value of M would now be equal to, so we have here one member here and another member here. So this is one member and this is the other member. Okay, so with that, guys, the value of M is now equal to 2. Okay, so what about for the support reaction? So we have a hinge support at the left side. So at the left side, we have here a vertical reaction and a horizontal reaction or a horizontal restraint. So with that, we have two reactions at the left side. And once again, at this portion here, so at this portion here, this is a roller, and a roller has one restriction, and that is the vertical restriction or vertical reaction. So counting the number of support reactions would now give you a number 3. So we now have here 3 support reactions. The next up, what about for the value of J? So for the number of J, since we have here 2 members, so for the number of joints, it would now be as follows. So we have here one joint here, another joint here, then another joint at this portion. So the joint is the edges of your members. So with that, we have 3. So meaning that J is, of course, equal to 3. Okay, so substituting all known values to our equation. So that is now 3 times 2 plus reaction of 3. This is equal to, or this must be equal to 3 times 3 plus C. Oh, by the way, what is C? So for C, this is the number of condition or equilibrium condition. And C is equal to 1 if we would now be having an internal pin. And C is now equal to 2 if we now have an internal roller. Okay, so if you're thinking, isn't this support here an internal roller? Actually, no. That is actually an external roller. When we say an internal roller, let's suppose that we have a beam here. Then from this beam, we have a roller that is being supported by, let's say, another beam. So this is what you would be calling an internal roller. So internal roller. Okay, so again, in this location here, this is not an internal roller. So with that being said, guys, the value of C is equal to 0. Okay? So with that, guys, C would now be eliminated. So substituting known values and calculating them, the answer here is 9, and the answer at the right side is also 9. And since we have proved here that 9 is indeed equal to 9, meaning that this beam is statically determinate. So when we say statically determinate beams, meaning that we can actually determine all of our answers using the equations under static equilibrium. Meaning, guys, we can use summation forces horizontal equal to 0, summation forces vertical is equal to 0, and summation moment is equal to 0. So just using these equations, we can actually answer our beam already. And we can solve for the reaction, solve for the shear and moment diagrams of that particular beam, and the like. So suppose that these are not equal. So in the situation we're in, 3m plus r is, let's say, not equal to 3j plus c. So let me just erase everything here. So once again, for example, that again, this is just an example. So suppose that for 3m plus r, suppose that this is 12. And let's say that 3j plus c is equal to 9. Since 12 is greater than 9, this is what you would be calling statically indeterminate. When we say statically indeterminate, you cannot determine the answers just making use of the equations of static equilibrium. So you need to have another, let's say, technique in order for you to solve for statically indeterminate beams. Though it would be stable, but of course it would be harder to solve for it. Okay? But however, guys, so suppose that in the equation, let's say that 3m plus r, let's suppose that this is 7. Then for 3j plus c, for suppose that this is 8. So since 7 is less than 8, or in this situation, it is less than 8, it means that this is unstable. Okay? So meaning that, well, you should not be designing or let's say designing or even analyzing those kinds of beams, because once again, it is unstable. So even without loads, it might get destroyed. Okay? But however, in our situation here, it was solved earlier that 9 is equal to 9, thus statically determinate. Okay. So, well, we already have a spoiler a while ago and even in the title. Okay, anyway, so since our beam is statically determinate, the next thing that we should do now is for us to solve for the reaction. So since we are to solve for the reaction, we would now, to call this, I would now be returning the loads here. And for the reactions, once again, we have a vertical force here, a vertical force here, and the horizontal force here. So I will name this as AH, or the horizontal component of the support at A, and I will be naming this as AV, and that would be the vertical component of this support here. And as for this point, I will be naming this as point B, and for its reaction, I will be naming it as RB. Okay? So let us now solve for these values. So in order for us to solve for AH, we could actually make use of the summation of forces equal to 0. So if we would be getting all of the forces which are acting horizontal at this beam, we just have AH and nothing more, meaning AH is now equal to 0. So meaning, guys, that in our case now, AH is, well, 0. So we do not have a value for AH. Okay, so what about for the vertical reactions here? So we have here AV and RB. So we could also make use of the summation of forces vertical. However, if you would be making use of summation of forces vertical, we would be having two unknowns, namely AV and RB. So if that is the case, you cannot actually solve for anything if that is your approach. So maybe in my approach here, I would make use of the static equilibrium equation of the summation of moment. So you could choose any point here. And if you would be choosing any point here, the summation of moment should be equal to 0. So for the sake of our class, maybe I would just be choosing this point here. You could also choose this point here. Your answer would still be the same. But again, since I am the one solving right now, I would be making use of this point. So with that, guys, the summation of moment at A, so again, this is A, that must be equal to 0. And as for my sign convention, I will be choosing counterclockwise positive. Clockwise positive. Okay. So what are the forces that if you would be holding this point would cause rotation? Okay, so this force here, 10 kilonewton per meter, this would cause rotation about this point. So again, if you would be holding this point and you would be having a force here, the tendency of this beam is that it would rotate in a clockwise direction. Okay. However, guys, it would be better if, let's say that since this is a uniformly distributed load, you should solve for first its resultant. Okay. So for its resultant, I will be writing them here first. So since this here is a rectangular load, its centroid is located at the center. Okay, it is located at this particular point. So meaning, guys, the resultant is located at this portion. Okay, suppose that this load here is rectangular. And once again, for its location, this is now half of 4 meters and that is 2 meters. So for this resultant, in order for you to get the resultant, just get the area of this rectangle here. So let me just erase my mess here. Okay. So with that, guys, this is equal to 10 kilonewton per meter times 4 meters. Okay. So that is the area or the total area of the whole rectangle. So that is basically 40. So 10 times 4, that is 40. But in my solution here, I will be writing the whole one. So, or the whole 10 times 4. So 10 times 4, that is just the resultant. And since we are solving for the moment, we must multiply it by the lever arm. When we say lever arm, that is the distance from your point, from the point that you are analyzing, towards the force. So it must be a perpendicular distance, and as you can see here, these two are perpendicular. So with that, guys, we must multiply this by 2, whereas this is the lever arm. Okay, so clockwise or counterclockwise, as you can see, guys, this force here would cause a clockwise rotation, and in our sign convention, clockwise positive. So again, this is positive. So what else do we have here? We also have the 15 kilonewton load, and we would be multiplying it by the lever arm. So 4 plus 2. So this is now the total distance. So with that, guys, 15 times 6. Okay, so what else? So we also have this force RB, which is actually unknown. And as you can see that this force is causing a counterclockwise rotation about this point. So as you can see, it is pointing upwards. And if you would be holding this point, the tendency of the beam is that it would rotate in a counterclockwise direction if this is the only force present. So it must be negative. Okay, so negative RB times the lever arm of 9. Okay, so where did we get the value of 9? That is 4 plus 2. So 4 plus 2 is equal to 6. Plus 3, that is 9. So the distance from this point to this point, that is 9 meters. Okay, so aside from that, we also have this particular force here that also causes rotation about this point. So, in order for us to get the resultant, so when we say resultant, of course, that would be a single force that would represent this whole, or the whole of this triangle here. So what we would be doing is just that we would be getting this particular area. And I will now suppose that in the centroid of a triangle, it is actually located at this point. Okay? So what is that distance? So if this is the whole length, if we are to measure it from the this side of the triangle, this is actually 1/3 of the total length. And with that, guys, this is now the 2/3 of the total length. Okay? So, and as for its area, the area of the triangle, that is 1/2 times base times height. So the base is 3 meters and the height is 12 meters. Okay? So with that, this is the force or the resultant. And for the lever arm, this is now our basis. Okay, so that is, so 1/2 times 3 times 12, or 1/2 plus 12 times 3. So I just interchange these two. And as you can see that this here is positive because this force would cause a clockwise rotation about this point. So that is positive. But once again, this is just the resultant. We must first multiply it by the lever arm. So as you can see here, this is the lever arm. So where did this come from? So since this is the location of the resultant, so if you would be getting the distance from this point to this particular point, that is 11. So where did that come from? That is 4 plus 2, so that is 6, plus 9. So 9 plus what is 2/3 of the total length. So if we are to divide that, guys, so the 2/3 of 3, this must be 2 meters and this 1 meter. So once again, if you would be getting the total distance, 4 plus 2 plus 3 plus 2, that is equal to 11 meters. Okay, so from that, let us now solve for the reaction. So you could use shift solve command, or you could also just transpose this to the other side and solve for RB. So I would just be doing that instead. So using my calculator on the left, so 10 times 4 times 2 plus 15 times 6 plus 1 half times 12. So 0.5 times 12 times 3 times 11. So we would be dividing this by 9. So again, that is by virtue of algebra. So the answer here is now equal to 40.88888 or 40.889 kilonewtons. Okay, so that is just RB. So this is now the answer here. What about for AV? So for the value of AV, you could also get the moment about this point. Or better yet, since you already have the value of RB, let us just solve for summation of forces vertical. So let me just rearrange this. Okay, so once again, this is the value of AV, and this is now the value for RB, which is 40.889. So getting the summation of forces upwards, and let us now, summation of forces vertical, and my sign convention is upwards positive. So I will be listing all of the forces from left to right. So on the left, we have here AV, which I assume to be positive. So AV, okay? So next up, aside from this AV, this force here would also cause vertical forces or vertical movement or vertical forces, so to speak, I should say. And again, since this is a uniformly distributed load, it would be better for us to get its resultant. So for its resultant, once again, that is the total area. So that is 10 times 4 or there 10 times 4. But if you would be solving for it separately, actually it is better. If let's say that you would be solving for it here, then this is 10 times 4. So that is 40. Just write 40 here. But since I have already written them there, there's no sense in me changing it. But it would still be the same, of course. Okay. So aside from that, going from left to right, you also have the 15 kilonewton load here, and it is acting vertically downwards. So negative 15. So what else do we have here? We also have here RB, and which I assume to be upwards. So plus RB. And you also have this force here. And once again, we have its resultant acting at this portion. And its resultant is its area, that is 1 half 12 times 3. Okay, so minus 1 half times 12 times 3. Once again, it is negative since it is acting downwards. So solving for it, so looking at the calculator to the right, I would just transpose everything to the other side. So in my calculator, or I could just also make use of the shift solve command. So that is alpha x is equal to, but actually I do not want to do that. Once again, I would just transpose it to the other side. So that is positive 10 times 4 plus 15 plus RB or minus RB, since I would be since I would be transposing RB to the right, and RB is equal to 40.889. And again, so minus 40.889 plus 1 half of 12 times 3. Okay, so the answer here is 32.111. So I just did the algebra in my mind. So if you do not want algebra, or if you do not want to do that and use the capacity of your calculators, so using shift solve, that is alpha x minus 10 times 4 minus 15 plus RB of 40.8889 minus 0.5 of 12 times 3, and this is equal to 0. So shift solve answer, the answer here is 32.111. So which is basically the same as with our answer here. Okay, so those are our reactions.